Hello everyone, for this tutorial video I like to explain how inductors by themselves behave when a constant alternating current signal is fed into them. As we remember from studying inductors previously, an inductor will attempt to maintain a constant current, so it will oppose any changes in current throughout the device. So this means the voltage is directly proportional to the rate of change of current and not the absolute current. Because of the fact the resistance of an inductor is more complicated than a simple resistance, it is given a different name, which is reactance, as a reference to how it reacts against the alternating current. The exact equation for the voltage across an inductor is voltage equals inductance times change in current over change in time. So if we looked at a chart like this, we can see that the current follows a simple sine wave pattern like AC signals usually do, but the voltage is out of phase with the current by the simple fact of how inductors generate voltages. So the voltage is at a minimum when the rate of change of the current is at a minimum and not when the current itself is at a minimum. And the voltage is exactly zero when the current is maximum or minimum, because the rate of change at those points is exactly zero. Fortunately for us, even though the two signals are out of phase, we do know the exact degree of the phase, which is that they are 90 degrees apart from each other. Because if you were to study calculus, then you would know the derivative of sine is cosine, and we know from trigonometry cosine and sine are exactly 90 degrees apart. And if we remember power equals voltage times current from a previous tutorial, we would multiply the waves at every point, and we would get an entirely different wave that looks like this. It may surprise you at first that there is such a thing as negative power, as this wave would suggest. But in the context of the circuit, negative power means it is giving energy back to the circuit instead of dissipating it like a resistor. Even though the instantaneous power may be different at different parts, if you were to notice how the wave is symmetric throughout its entire journey, then the total power dissipated would always be zero, regardless of the power dissipated in a specific instant. And because we remember previously that inductors oppose a reactance against a change in current, we can state the greater the change in current, or the greater the frequency of the signal, the more reactance the inductor will have, and also the more inductance, the more reactance, because more inductance means more opposition to change in current. So we would state x sub L equals 2 pi times frequency times inductance. And we should also see too that the opposition is not a simple number or scalar, but actually a phasor, because of how the voltage and current are always 90 degrees apart from each other. So this means that we would either have to convert them to rectangular form as shown in the previous video, or figure out a way to make them the same angle, which would obviously involve changing the scalar value of one of the numbers, or magnitude. Now that I've explained all of the relevant factors to a single inductor with AC in it, I can explain a circuit with a resistor and inductor, before moving on to even more complicated circuits. Don't forget to subscribe if you found this video informative, and make sure to see other tutorial videos, and follow me on either Facebook or Twitter for more content.